Hello everyone, it's Benny, and in this video we're going to be solving the Quaternion paradox. And you might be wondering, what is the Quaternion paradox, and why on earth should I care? Well, here's the thing. Let's say you go out on the internet and you start searching for what Quaternions are or what they mean. Without fail, you'll come across one of two things. Either you'll come across a site that says, oh, we're going to talk all about Quaternions, but we're not really going to explain what they are or what they mean. So if you're interested in that, go look on the internet. There's plenty of good information out there. Or you come across option B, if you're really lucky, which says, oh, Quaternions, some BS about four-dimensional hypersphere. You want more information? Go look on the internet. There's plenty of good information out there on it. So, yeah, that's the paradox. No matter how much you search for information on what Quaternions are or what they mean, the only thing you find is information telling you that there's plenty of information about what Quaternions are or what they mean. And that doesn't really help anyone all that much. So today, I'm going to be explaining what Quaternions are and what they mean. And in light of this, I'm going to sort of do it in two different ways. I'm sort of going to explain it twice, if you will. The first way I'm going to explain it is sort of the intuitive way. Just how can you visualize a Quaternion? How can you intuitively grasp this four-number nonsense, you know? So that's what I'm saying. Just how can you understand it without having to get into all the mathematical details of this is how the mathematics has to work out because of insert ridiculous nonsense equation here. And the other way, of course, is going to be a little bit more of the mathematical way. How do you understand all the numbers? What do the four numbers actually mean in terms of that sort of intuitive idea? I'm not going to go into the sort of in-depth derivation of what a Quaternion is, because, let's face it, there's plenty of good information on that out on the internet somewhere. So if you're interested in that, I'm sure you can find the in-depth derivations out there somewhere. And if not, hey, maybe I'll come back and solve the Quaternion paradox 2.0 if someone's really interested in that. But for now, that's what we're going to be doing. So with that, let's go ahead and let's get started. So, I'm going to talk about the intuitive idea of a Quaternion. And that sort of starts off with the intuitive idea of a directional vector, because Quaternions and three-dimensional vectors are completely identical with one key difference. So, kind of makes sense to start with a vector. And if you already understand vectors, then you may or may not, it's up to you, but you may want to stick around anyways, just because this is going to sort of lead into the intuitive idea of a Quaternion. So, what's the intuitive idea of a three-dimensional directional vector? Well, as you may know, a vector is pretty much just a point. It's like an xy coordinate, or in the case of a three-dimensional vector, an xyz coordinate. The key difference being, it can also be interpreted as a direction. So, it's like a line from the origin, and the end of the point is like the head of an arrow. You can think of it like you're pointing at something. Just hold your arm out and point at something. There's two ways to interpret that action. Either you're talking about some physical point at the exact end of your fingertip, or you're talking about something in the direction that you're pointing. That's the idea of a directional vector. There's two interpretations of a vector. There's position, which would be the exact end of your point, or directional vector, which would be something in the direction that you're pointing, or more generally, just the actual direction you're pointing. So yeah, that's the intuitive idea of a directional vector. Think of it like pointing. The direction you're pointing, there you go. And the intuitive idea of a Quaternion sort of stems from that. And here's how I like to think of it. Let's say you're out on a camping trip, and here's my amazing campfire. And here is you. And you have a stick because, well, you're cooking s'mores over the campfire. And here's the thing. You get a little bored after a while, and you decide you're going to play with the s'more stick. And can't really draw that in a static image, but, you swing it up, you swing it down, you swing it wherever. And here's the thing. You can represent any of the directions you swing it with a directional vector, but what if you twirl the stick so that, you sort of, don't know if I can draw it, but, sort of twirl it. You notice the s'more rotates with it. A directional vector would only capture the direction, but you can still affect the s'more without changing the direction you're pointing it in. Kind of like you can stick your finger out, then you can sort of twist it. That is the W component of a quaternion. W as in twirl. And that's the difference between a quaternion and a directional vector. And I'm not kidding. That's it. That's the intuitive idea of a quaternion. It's exactly the same as a directional vector. The x, y, and z are a directional vector. The difference is the W component, which represents the twirl. How much have you twirled the direction, like you're rotating that s'more over the campfire. There you go. That's it. I'm not kidding. It has nothing to do with some four-dimensional hypersphere nonsense. That's a quaternion. The x, y, and z, that's the position or direction, depending on how you want to interpret it. So, direction, W, it's the twirl. There you go. That's the intuitive idea of a quaternion. And if that's all you care about, you can stop watching right now. But now I'm going to talk a little bit about how that works mathematically. Now we're going to talk just a little bit about the mathematical idea of a quaternion. What do the actual x, y, z, and w components actually mean? I mean, we know now that it's this idea of some direction and some rotation around this direction. But how could we take, say, those x, y, z, and w numbers, and then figure out, well, what is that direction? What is that rotation? How could we do something like that? And that gets a little bit interesting, because quaternions, mathematically, depending on your background, they may or may not be a little bit tricky to grasp the mathematics that go into it. It's not hard, per se, it's just a little bit... It's not the way you'd think of it first. So, in light of this, I'm going to be assuming a little bit of mathematical knowledge, so that I don't have to go and re-explain a bunch of basic math, and I can just keep this focused on quaternions. So I'm going to assume, for the purpose of the mathematical explanation, that you understand math at least up to trigonometry. So you know how algebra works, you know all that stuff, you know arithmetic, of course. And you don't need to know every trigonometric identity under the sun, just as long as you understand what sine and cosine are, and how they can be used to find an x-y coordinate, you should be good. That's enough trigonometry. But it's important to really understand how it relates to angles and whatnot. So, you need that. You're of course going to need to understand a little bit about vectors, because, well, like I said, quaternions, for the most part, are directional vectors, just with a little bit extra. So if you don't understand vectors, you're going to have quite a time understanding this video, or at least the math. And lastly, you're going to need some idea of complex numbers. At least understand how the imaginary number just means, oh, it's just a number like normal, except it's in a different dimension. It's in the second dimension. It's the y-coordinate rather than the x-coordinate or whatnot. So understand that, and also understand that multiplication, how multiplying two complex numbers will result in a rotation. It will rotate the complex numbers. So if you at least understand that, you should be okay to understand the math. Like I said, I'm not going to go really in-depth in this is how you derive the exact equations. My main mathematical focus in this is, what do the numbers mean, and how can you use them in a useful way? That's my big thing in the mathematical section. So, with that, let's start talking about the mathematical idea of a quaternion. Now, just in case you've never seen a quaternion written out before, it looks a little bit something like this. You have an x, y, z component, and of course rw, the toroidal. But we also have this I, j, and k. Those I, j, and k, those are imaginary numbers. They're imaginary units. They're just to indicate, oh hey, the I represents the x-axis, so the x is on the x-axis. The j represents the y-axis, so the y is on the y-axis. And of course, the k represents the z-axis, so the z is on the z-axis. That's their only purpose. For this video, I'm actually going to represent them in sort of the way they are done with vectors, which is I hat, j hat, and k hat. Because I personally think if you don't have that there, it sort of gets confusing as to whether they're numbers you're multiplying by, well, real numbers you're multiplying by, they're just variables, or if they're imaginary units. And I just don't want that confusion, so even though it's technically not proper notation, I'm going to put the hat there, just for that distinction, just so you don't get confused and think, oh, I'm multiplying this by some k variable. No, that's the unit. That represents that this number is on that represents that this number is on the z-axis. And this represents that this number is on the y-axis, and this represents that this number is on the x-axis, etc., etc. Now that we have that out of the way, there's one more thing I want to clear up. If you set the w component to 0, if you just get rid of the w component, you have a vector. I'm not kidding you. In fact, that's how vectors were originally created. Someone took quaternions and just got rid of the w component, just said w is always 0. Or w is always ignored, and then you have vectors. So that should tell you a lot about what a quaternion represents right off the bat. The x, y, z components, they are a vector, just like you know and love. So don't start getting confused and thinking, oh, they're vectors, but they're not vectors because they're quaternions. No, x, y, z, that's a vector. So that also leaves the question of, well, where do quaternions differ? If vectors are just quaternions with the w at 0, how does the w change things? And here's where it changes things. And here's where the main focus of the video is going to be on, or the main focus of the mathematical part of the video is going to be on. The way quaternions can be changed is when you start representing a rotation with a quaternion. When you start saying, okay, this is a rotation. And it works pretty much like you'd expect. The x, y, and z represent the direction, the w represents the rotation around that direction. But it's not... But there's a little bit more to it than that, I should say. Here's how you might think of it at first. You might say, okay, the x, that's my x vector. So, just, I don't know, so... Actually, I'll put it like this. You might say, okay, I have some vector, I'll say d for the direction, and that is my x, y, and z. And you might go, okay, cool. And then w, that's just some theta, some angle. Maybe it's in radians, maybe it's in degrees, whatever, it's an angle. And here's the thing about quaternions as rotation. Technically, that's true. It's just they aren't represented exactly as you might think. The angle isn't some angle in degrees or radians, and the x, y, and z, they're a vector, but they're not a unit vector. What you have to do to make this valid, because this is technically valid, is w is the cosine of some angle, and the directional vector is that unit vector times the sine of some angle. And you might be wondering, why on earth is this? And like I said, yeah, this is still representing exactly the same way. This is a vector, this is an angle, but it's not quite how you might think, because there's sine and cosine involved. You might think, well, what on earth is this nonsense? Why on earth do I need sine and cosine stuff in here? Why can't I just have my angles, man? And that has to do with the complex part of it, because quaternions are technically complex numbers. And when you multiply complex numbers, that performs a rotation. That's why the sine and cosine are here, because you want that sine and cosine in there so that when you do the multiplication, which I'm not going to derive for you, again, there's plenty of information on the internet about derivation if you want that, but we do need the sine and cosine in there so that we can do complex multiplication, so that we could take quaternion A that represents some rotation and multiply it by quaternion B. And then we have a quaternion that represents the combined rotation of A and B. Then we can take that, multiply it by rotation C. Then we have a quaternion that represents all three rotations in one quaternion. And stuff like that, doing powerful things with complex multiplication. And it might not be intuitively obvious how having sine and cosine in here would have anything whatsoever to do with that. And that's where the complex number stuff comes in. So I'm just going to start with a basic complex number rotation, a very basic one, just for simplicity's sake. And then I'm going to show you how that applies to quaternions and how that causes that sine and cosine thing to matter. Thank you, menu, but I actually want to draw. So let's say here's my graph. I know, I'm being picky, but whatever. This is my imaginary axis. This is my real axis. Let's say this is my rotation. I want 45, oh dear, degree rotation. Now you could figure the... Thank you. Now you could figure out the rotation for that with sine and cosine, but since it's 45 degrees... Well, I should say, you can figure out with sine and cosine and get square root of 2 over 2 plus square root of 2 over 2i, but for simplicity's sake, I'm just going to do 1 plus 1i. This will technically do some scaling, but I just want to keep the math as simple as possible so that I can demonstrate the concept. And let's say what I want to rotate that by is the 4i. This is my point, 4i, actually just 4i plus 0. Just for simplicity's sake, because that's really easy to visualize. So it's 4 units up here somewhere, there's my point. After rotating 45 degrees, it should end up, well, somewhere over here. Plus some scaling, because I'm using 1, 1, but you get the idea. So, how on earth would I rotate this? Well, as you should know if you're watching this video, rotating complex numbers is just multiplication. 1 plus 1i plus 1i times 0 plus 4i. That gives me the rotation. And if I rotate these, then I get 1 times 0 plus 1 times 4i plus 1i times 0 plus 1i times 4i. And of course this simplifies to 0 plus 4i plus 0, because imaginary 1 times 0 is still 0, plus, and I times I is negative 1, so I should say minus 4. So that gives us our new rotation. Negative 4 plus 4i. And if I go negative 4 units that way, and then 4 units up, that's indeed a 45-degree rotation that way. So, as you see, dagnabbit, that's complex rotation. And you might be wondering, cool, I know complex rotation, why on earth did you just show me that? Here's the thing, vectors are numbers too. So, what we could do, if I move over a little, is we say, okay, thank you, menu. We say, okay, our W is our real component, plus d hat as our vector. So we can treat our quaternion as a complex number of just w as the real component, and our vector as the imaginary component, because vectors are just numbers. So it can be treated as the imaginary number. And the reason we can treat it as an imaginary number is because our x, y, and z are all based on imaginary axes. So, because of that, I can treat that as just any hecknabbit, as just a typical complex number. And then I can do complex multiplication to get rotations as such. Now, this, you might think that's a mathematical trick, and it is, and it won't work normally. And the reason goes back to this. I have an angle, I need some complex number that represents it. I sort of cheated a little here, but like I mentioned, the way you'd normally do this is you take cosine of 45 plus sine of 45 times I. And that is why the sine and cosine are there. That's converting the angle. That's putting the angle in this sort of... Why did I make a second one? I don't know why I made a second one there, so let's just ignore that. But actually, is my eraser mark? No, okay. So yeah, just ignore that. But that's why I need sine and cosine, because that's how I put the angle into the complex number. Cosine of angle times w plus sine of angle times d hat. And that gets me my quaternion as a complex number, which means this is perfectly valid for rotation just by multiplication. That's why there's the sine and cosine here. There you go. And that's how you represent a rotation with a quaternion, and that's why it's represented that way. You can multiply them together, and you can just concatenate rotations like that. That's all there is to quaternions rotations, folks. If you wanted to, you could do some fancy substitution in here, and then try figuring out what the exact rotation numbers are. And of course, I did that. That's what I used in the equation I used in the game, but that's how the quaternion representation works mathematically. There you go. And I'm sorry, I completely forgot to mention this, but right here I wrote cosine theta times w, where it should actually be just cosine theta, because that's where the w comes from. The w is coming from this sine cosine thing. It's not like there's something already there that it should be scaled by. I'm sorry. So it should just be w is cosine theta, not w times cosine theta, because this is defining w. I don't know. I'm sorry, that just completely slipped my mind. I was in the heat of the moment, I guess. Because, yeah. So like I said here, w is cosine theta, and the reason it's cosine theta is so that it can be in this complex multiplication for rotation. So now that that's cleared up, let's talk about some oddities you may have seen when working with or hearing about quaternions. For example, you might have heard someone say something like this. Yeah, sure, you have the d vector. Yeah, sure, you have the w component. And yeah, sure, they're set based on sine and cosine, but they're not set to the angle you want. They're set to the angle you want over 2. And technically, this is one way you could work with quaternions. It's just all the rotations would be half of what you're actually looking for. And you might be wondering, well, why on earth would I want all my rotations to be half of what I'm actually looking for? And the reason is if you're planning on rotating a vector by this quaternion. So, for instance, let's say this right here is some quaternion q. So, let's say I have some vector v that I want to rotate by quaternion q. Now, the v component, the w component that I add onto this vector, because I'm going to have to add some w component to multiply it by a quaternion, I'll add on some w component. I think it has to be 0. It might have to be 1. My memory may be failing me here. I'm sorry. So it's one of the two. I think it's 0, but you'll set the w component to something like that that's relevant, and oh, good lord. And then you'll multiply by q as the v was a quaternion. And that will rotate it by half of what you want. It will also add in the imaginary nonsense that you're not interested in. So what you'll do is you'll take the conjugate of q and multiply it by that, q conjugate. And what that is, whoops, I'm sorry, just ignore that, I guess. So what that is it's the same as q, except x would be negative, y would be negative, and z would be negative. So just basically take the x, y, z component multiplied by -1. Basically, think of it, q conjugate is negative d times that. That is q conjugate. And the reason you'll do this is because then it will still have all the same scalar values, so it'll still have the values critical for the rotation, but it's negative. That cancels out all the imaginary nonsense, and then you have the full rotation, you don't have any of the imaginary stuff you didn't want introduced, and you have the fully rotated vector. So there you go. That's the reason you'll sometimes do it as over 2. And that's the neat thing about this. All of this is... theta over 2 is still a valid quaternion. It's just if you concatenate all your or multiply all your quaternions with half the angle, the final quaternion you get will have half the rotation you're looking for. And yeah. Now, the final thing I'd like to do is I'd like to show you how to, I don't know if I want to say visualize, but just look at some quaternion and then figure out how that would look. How would that rotation look? What is that rotation? So, let's say I have some quaternion, and I'm going to do this 2 ways, by the way. First, I'm going to do it mathematically, then I'm going to show you how you can sort of just do it in your head if you want. So mathematically, if you need to draw a graph of it for some reason. So, first off, q is some x times I hat plus some y times j hat plus some z times k hat plus w. This is your rotation. I'm not going to use concrete numbers here, just because I'm wanting, this is so you can actually do it with math if you want to. And what you'll do here, thank you, what you'll do, first off, just take x, y, and z, and use it as a vector. So now you have this. And what you want to do is you want to normalize this. So just take the length of v. So actually, yeah, I'm doing it right. So take that. So what I should say is, whoops, v is the x, y, and z divided by the length of that vector x, y, and z. And that's what the absolute value means. So, yeah. So, in other words, normalized. Wait. Spelled with a Z, isn't it? There. So, what did I just do? Oh dear. Okay. So you start off with the normalized vector. That took way too long, but anyways, you have the normalized vector v. Now what? Well, now you have the direction, so you can sketch that out in 3D space. So this is my 3D space, and this right here is my direction. And that's the first piece of information you need for the quaternion. In fact, it's half the information. All you need now is w, the twirl. How much am I going around this axis? And the way I like to usually represent this is I like to have two graphs. One of the direction and one of the rotation around that direction. So, but again, this is just me. You may need to do it some other way, but This is the way I like to do it if I am given a choice. So this is the direction, and w, well, remember, w is the cosine of theta, so I'll take cosine, the inverse cosine of theta, and that will give me my x component. So x, well actually I should use different variables, so let's say a, and let's say this is b. So a equals the inverse cosine of that. And here's the thing, if you have a normalized vector, well, you should be able to figure out what the length is. The length. So I should say that, and then b, and remember, what's length? It's going to be a normalized vector. There. Okay, v is the direction it's in, the length is the sine. So take the inverse sine of the length of that vector of x and y and z. And with that, you now have the 2 points, and with that you can figure out where it is on the unit circle. And from there, you can figure out, oh, it's a rotation by this much. Well, I should say this much. So, there you go. And now you can figure out theta. And there you go. That's how you can visualize a quaternion. You can figure out, oh, hey, this is the direction it's in, and that's the rotation. And of course, if you're doing the over 2 stuff, then you're going to want twice that rotation. So, yeah. And now, from here, this is what I like about doing this way. Now that you've seen the sort of mathematical way of doing it, how you do it on your own should be sort of intuitive, shouldn't it? The direction, x, y, and z, is going to be the same no matter what length it is, so you can figure out the direction pretty easily, just sort of intuitively. And as for the rotation, w, well, I'm not going to lie, you may, depending on how well you understand sine and cosine, need to whip out a calculator for that. But if you have an idea of how sine and cosine work, you should be able to figure out, okay, it's going to be rotated. Well, 1 is no rotation, so as it goes down, it's going to be rotating a little bit more, and so forth and so on. And you should be able to get a pretty good idea of how much it's rotating around that axis. And, yeah, so there you go. That's quaternions, that's how they work, that's why they work, and that's how you can sort of figure out what it means. So, hope this helps you. Hopefully now you understand what quaternions are, why the way they are, and how they work. And hopefully you don't find them nearly as scary as you did before, because quaternions really aren't that hard. If you still find them hard, then I'm sorry, I probably just haven't explained it very well. I'm not much of a math teacher myself, but yeah, hopefully this helps, and thank you. See you next time.